So we got this best compromise between the cut or the various variants of cutoff. And if you're wondering how this
Prem, just
cutoff would actually,
sorry to interrupt, Prem. The
yes,
screen, your screen is not visible.
oh, sorry.
Yep,
Right.
now it's there.
Okay, thank you. So if you're wondering how this particular cutoff is implemented, I would like to show you a schematic. So I've taken a system of say 9 particles in it, and I want to look for the implementation of cutoff for one selected particle. Say for example, I want to look at the force acting on this red particle. So what I'll do is I'll quickly measure the distance between this red particle to LU1, the red particle to orange one, and all the other particles. So after knowing all the distances, I would qualify only those particles whose distances are lying below R cut. So I'll simply draw a circle around this particle, and this radius is nothing but the cutoff radius, and whichever particles fall inside the radius of inside the circle are qualified for computation for force computations, and those particles which are falling outside the circle were disqualified for force calculations. And if you wonder what about this particle seems to be lying on the circle, but to be frank, the particle that you see here has got its center slightly outside the circle. So whenever we see a particle, we only consider the center of the particle. If the center of the particle is on the circle or inside the circle, we'll consider that to be qualified. Otherwise, it is disqualified. So you can see that although there were 8 possible pairs forming with this red particle, we have qualified only 5 of them. These 3 particles stay disqualified. So this is a kind of improvisation that we have in our code, so that if we just disqualify these particles in the very measuring distance level itself, we need not unnecessarily calculate slopes and forces for these particular particles. So we'll just carry on this particular concept to a next level, that is minimum image convention in periodic boundary conditions. So I was talking about the same system with 9 particles here, and this system has got its periodic images all around. So you could see all these 8 images around the central system of our focus. And now I want to implement the periodic boundary condition, and also wanted to calculate the force experienced by this particle because of the presence of all the particles. When I say all the particles, I'm not just looking at this box alone. I want to capture the effect of all the particle images which were around the master box. So this is the main system, and these are the images of the system. So when I want to see for a particle and the force acting on this particle, I will have to consider all the particles which are around it, including the image particles. So at the starting of this concept, it would seem to be a little crazy because we want to study a system of 9 particles for which we are additionally taking up 72 more particles into our account. So this sounds crazy because we have unintentionally increased the number of particles and the computational requirements of our scheme. But after a little understanding, or after looking at this with little more deeper, we can actually capture the essence of this scheme. So let us look at this red particle. So we can find out that these 5 particles were standing inside the circle, so we can qualify them. And other 3 particles which are belonging to the system were standing outside the circle, so we can simply disqualify them. And when I want to calculate force acting on this red particle, I would only consider these 5 particles, leaving all the other 3. So you could also see this is the reference particle I've taken, and all these 5 particles, their separation distances were represented here. And based on their separation distances, I can calculate the force between red and blue particle by taking the slope here, between red and yellow particle by taking the slope here. So all these particles were standing outside the actual cutoff limit. So therefore, I'll not have these particular particles in my force computation at all. And I would like to show you another example by taking a particle from the same simulation box. So this time I've chosen this particular particle. And if you observe this particle, I'll have to compare, or I'll have to look at the particle, this particle, and its separation from all the other particles within the system. So this is what I do. So this particle has got the separation distances like this, and these separation distances I've mentioned here as well. So the 4 particles that you see here are directly inside the circle, and other 4 particles were standing outside the circle. So we can straight away disqualify these particles, but when you remember, if you could remember, I've told you that when we select a particle, we should also look at all the possible particles that we have in the surrounding images. When we have taken the red particle, the circle is just confined to the system itself. Because no other particles were coming into the circle, we can simply ignore them. But here in this case, the circle or the cutoff radius corresponding to this particle encapsulates few other particles from surroundings or neighboring cells. So what we do is, since we have to disqualify this particle, we were looking for its image, if possible, if any of its image is available in the close proximity, we would discard this and consider its possible image. So we have ignored this particle and we have taken its image, and its image is likely lying on the circle. So we can ignore this particle, but as a remedy, we can just switch on to another particle, which is its image. And by doing so, we have taken this system into consideration, this image into consideration. So this particle is also under the influence of these image particles now. And similarly, if you could observe, the yellow particle is standing disqualified in the parent cell, but when you look at the image, it is quite close. So 2 additional particles have crept into our calculations, and this means that the particle which you have taken here has the influence of surrounding particles as well. So if I take this pink particle, few particles from the main cell would get discarded because of their larger separation distances. But if you observe, this particle is quite close to the pink particle when I take the image. So by image consideration, I would capture this particles effect or the image of this particles effect into my system. So this is the actual essence of periodic boundary condition. So with this basic information, I'd like to take you into the basic elements of our MD simulation algorithm. So these steps I've been repeating for quite a good number of times now. And the very first step that we have in this algorithm is initialization. So in the initialization process, we'll have to define the system boundaries. So you might have been already working with this assignment also. So we have the box minimum and the box maximum dimensions along X and Y directions, which I have made it as 0 and 10. So my box will be 10 units large or 10 units long and 10 units high. And the number of particles I want to accommodate in this box are just 3 along X direction and 3 along Y direction. So this is a 3 by 3 matrix kind of arrangement. So I'll have altogether 9 particles. And for all these 9 particles, I'll have to provide with the initial positions and initial velocities. And mind you, I've just given a random set of velocity values to these 9 particles along X and Y directions. And I'll have to define the time step, which is 0.05 seconds in this particular case, or 0.05 time units in this particular simulation. And the maximum number of iterations I've limited just to 10. And the boundary condition I'm planning to incorporate into my system is a periodic boundary condition. And epsilon and sigma, remember, epsilon and sigma are the values of LJ potential curve. So those I've given as 5 and 2.5. These are arbitrary values, but if you are focused towards simulating a particular system, you'll have to choose this epsilon and sigma values corresponding to that particular material in the system. And mass is the atomic mass of the particle, which I've taken as 0.5. This is again a random choice, but these 3 values will purely depend on the material that you're going to simulate. So this is the initialization process that I have in my hand. So with this initialization process, I'm good to go with the next step. So because giving you coordinates of all these particles and the velocities of all these particles is not really convenient, I want to bring a pictorial representation of these particles. So these are the 9 particles that I'm talking about. And the next step is possible pairs. So we have to look for the possible pairs. And for doing so, we'll require the concept of minimum image convention. And after looking at minimum image convention also, we'll have to qualify only those pairs which have their separation distance less than the cutoff. So basing on these particular aspects, what I'll do is I'll just take one particle and I'll calculate the separation distance from one particle to all the other particles using this simple formula. And I've tabulated all the possible pair distance map. So if the distance of separation between particle 2 and 1 is 3, particle 4 and 2 is 5.83. So likewise, I have measured all the distances. And if you could observe, there is symmetry in this particular calculations. Distance between 2 and 1, distance between 1 and 2 are both same. So I can only calculate these values. So all these other values I can simply copy from here. So this also kind of gives us a flexibility in counting and calculations. So with half the number of calculations or less than half the number of calculations, I can actually compute distances of separation between all these particles. So remember this particular lower triangle pattern, and we are going to implement this in our algorithm. So basically, if I start with the first particle, I did not start comparing the first particle distance with the first particle. I'll have to compare the first particle distance with the second one, which is also equal to the second particle's distance with the first one. So this kind of gives us unrepeated combinations for particle pairs. The next step that we're going to look at is calculation of forces between the pairs. So since we have the distance of separation, we can simply calculate the potential at that particular separation distance and use that potential for calculating the force. And if you have observed, all these values were now changed to the force values. And in this case, I'm showing you only the force along x direction. So after calculating the force, I'll have to take its component along x direction and component along y direction. So these forces which I'm showing you here are only the components of forces along x direction. The y component forces are computed, but just to avoid cluttering of all the data on single slide, I have not shown them here. But a very similar chart is also prepared for calculating the forces between all possible pairs. And again, if you observe, the force acting between particle 2 and 1 from 2 to 1 is nothing but the force acting between particle 1 and 2, but in opposite direction. There is only change in direction. So again, in this case, we can actually have less than half the number of calculations done to completely map this possible pairs. So this is a kind of skew symmetric matrix that we obtain in this force calculation. So once we are done with force calculation along x and y directions, because this is today we were confining to only x component and y component of forces, which are these, we are good to go with the next step. And in the next step, what I'll do is I'll just take one particle and all the force and the force acting on this particle because of all the other particles presence, which is sum of all these x components. I'll just add them and I'll record them next to first particle. So this is fx force, which I get if I add all these particular force components because of all the other possible pairs. So that is what I've done here. For the first particle, forces along x direction is this, force along y direction is this. So these two are the two components of first particle's force. And similarly, I can calculate for all the other particles in this list. Next thing that I'll be doing is I'll update my velocities and positions based on forces. You might have already seen these particular formulas in the previous class. And this is a velocity overlay scheme based on which you can update your velocities and distances. I've used a simplified version here. From force, I can actually calculate the velocity, and from velocity, I can calculate the position. And these are the new set of positions that I have for my particles. If you see, after this updation process, these particles would slightly move to the new positions. So the particles have moved to the new positions. And now with the new positions taken into account, we'll have to repeat all these steps. So repeating steps from all these 2 to 4 is what we have as a fifth step. And we have to repeat this until we get the convergence criteria met or the stopping criteria met for our simulation process. So these are the elements. And now I'm interested in showing you the actual doing of this MD simulation. So what exactly are we doing in MD simulation, the coding aspect of it? So I've done this coding in C programming language, but you can pretty much do the similar things in any language that you're comfortable with. And what I'm presenting you here is just a pseudocode, meaning that this is not fully functional code, but it would just have those lines which are required for representing the features available in the code. So this will not run because I have skipped all the initializations and the headers files and all the other things. So this is just showing you what I've done and the logic that I've implemented in my scheme, in my molecular dynamics simulations code. So the very first thing that I've done here is I've initialized the position of particles in x and y directions. So px is an array which I have used, and this condition sets all the particles in x direction, and this condition sets all the particles in y direction in an array sort of thing. If you observe this simulation, at one point all these particles will have a very organized fashion of arrangement, and that is the initial state from where this simulation has started. And that initial state was initial positions of all the particles were given from this particular step. The next step is to assign random values to velocities along x and y directions. So the moment you see these particles moving, they were actually given x and y components separately for every particle, and I've created the random numbers. I've used the random numbers concept to generate velocities randomly to all the particles. So once I have created all the particles, the velocity for all the particles, I've not straight away given those velocities to these particles. Instead, I have done some simple adjustment to these velocities. So I've calculated the average of all these velocities in this case, and I've subtracted the particles velocity with average. So I would like to answer to this logic once I complete the session. So in the meanwhile, you please think on it, why I have done this particular step. So what I've done is I've taken the average of all these particles, all the particles velocities I have from the random numbers. These random velocities were averaged along x and y directions, and all the x direction velocities were subtracted with the average value, and all the y direction velocities were subtracted with the average value along y. So I want you to think on this particular step and tell me after this lecture is over why I have done this particular step. So moving on, after I have the initialization process done, the next step is calculation of the forces. And before calculating the forces, I require the distance of separation between all the particles. So I have taken the positions of two different particles, I and j. And if you observe, I have the selection process done in two different loops. I'll select one particle with outer loop and the other particle with the inner loop. So outer loop can run from I equal to 0 to n minus 1. If I have n particles, the outer loop limit is n minus 1, and the inner loop limit would start from I plus 1. So I'll start with the next particle. Say for example, if I have the first particle selected in this particular case, I'll not start with the first particle in second pair. So if I have to start with the pair comparisons, I'll not take 1 pair, I'll take 1 2 pair. So if I start with 1 here, I'll have to start with 2 from its counterpart. So whatever value I have here, I'll just take one additional value to it, and then I'll start the loop. So this is again a very simple thing. I have calculated the dx value, dy value, and if you see here, I have dx equal to dx minus box L. Box L means length of the box along x direction, round dx by box Lx. So this is a very simple technique which is used for looking at minimum image convention. So I'm checking the distance, and I'm checking if any other particle is available to me which is closer than the existing particle. So this will give me the least the particles. It will compare all the images that we have in a system and give me dx as a value of least distance available between the particles. When I say particles, the particle 1 is compared with all the possible images of particle 2, and then it will give me the least possible distance between 1 and 2. The second particle could be the original particle, or the image of second particle can also be considered here because of this implementation. So this is basically for accommodating minimum image convention. And then I'll calculate the square of this particular separation distance. Under root this is r. So square is this much, and I'll compare that with cutoff radius. So this is cutoff radius. And so instead of taking the square root of this particular parameter and then comparing it with cutoff radius, what I've done is I've taken the square of this particular distance, I've taken the square of cutoff radius, and I've compared the squares straight away. So after comparison, if this cutoff radius and r square, or the distance of the separation distance square, they are not qualifying, they'll just get discarded. Only the qualifying pairs would enter into this. And for those qualifying pairs, I have the force calculation here. The force is calculated. I've taken the derivative of the potential and then I've written it here. So this will accommodate the particles forces in appropriate bins. So for ith particle, the calculated force would go there. For jth particle, the negative of this force would go there. Similarly, along y direction, I have the same thing. For ith particle, the force would go there. And for jth particle, the negative of this force would go there. And remember, uh, after I have 1 2 pair, I'll have 1 3 pair. So 1 force experienced by 2 on 1, force experienced by 1 on 2, both of them are calculated. When I have 1 3 pair, force experienced by 1 on 3 and force experienced by 3 on 1 should also be considered in 1. So every time I take these force computations with different pairs, I'll have to append those values to the existing values. So that's why I've taken this summation to the existing values. So this is how I calculate force. And after I'm done with calculation of the force, the next step that I will do is updating the velocities and position. This is a simplified version of velocity overlay. I'll simply multiply force with time step, and divide with mass. So this is nothing but a dt, and I'll add that to the existing velocity along x and y directions. And from velocity updated values, I'll just update the positions. And after doing so, I'll check for the periodic boundary condition. So if position has crossed box length, I would bring it back into the box along x direction, along y direction. So this is basically doing that job. And then I'll repeat this process for nth number of time steps or for nth number of iterations. And once I'm done with all that, I can have a simulation similar to this generated. So this is the pseudocode that that would simulate all the particles behavior in 2 dimension. And if you want to extend that to 3 dimension, you'll have to accommodate corresponding equations for the 3rd dimension as well in all these steps. And in the next slide, I just want to show you the task that we have taken for the previous session. So this is a 1 particle simulation which I have coded in Excel. So clicking on this PBC would initiate the process, and the particle would start moving from one position, and the initial position and velocities were given here. The time step, maximum iterations or the maximum number of iterations, box length, all these inputs were given. And this is the current position of the particle, and this is the current velocity of the particle. I want you to observe the particle when it hits the boundary. So the velocities will never change as I am on periodic boundary condition. So the particle will get lost from one particular side and appears from the other side. And I can start with reflective boundary condition. And I also want you to observe these velocities when particle hits the wall. So when particle is hitting the wall, the velocity sign got changed. So this is the reflective boundary condition, and the positions were automatically adjusted to the new velocity, and the patterns would actually have the implementation of reflective boundary condition. So this is for one particle, 2 dimension MD simulation. But if we want to have more number of particles, then we can have a little robust setup. So in this case, again, I have the initial box limits. I have the particles count here along x, along y, I have this particular number of particles. Time step, maximum number of iterations, periodic boundary condition as the kind of boundary condition, the value of epsilon and sigma, mass and values. So these are the columns dedicated for position of particle, x and y positions, and vx and vy are the velocities along x and y directions of the particle. So initially, these positions will result in very schematic arrangement of particles along 4 by 4 array kind of arrangement. And these velocities initially would be random velocities assigned to them. And the force computation would not start in the very initial step. So I want you to see the animation and observe the behavior of particles in this animation. So particles have started from organized pattern. And every time we start the animation, the forces get computed by themselves based on the scheme that we have talked about in the previous slides. And the velocities were getting updated and the positions were getting updated, and you could see the representation of all these changes of the particles in this plot here. So this is basically periodic boundary conditions. So the particle is free to leave from this particular end and would reappear from the other end. So we have reached the limit of maximum iterations, so the simulation has stopped now. We can increase the number of iterations, and then we can still have prolonged versions of this particle behavior being observed here. So I'm planning to share these sheets with you. Feel free to explore these options and then see different setups. And if I can have something like this, you can see the particles behaving in a strange way when I have unequal values of particles along x and y directions. See, one of the directions will dominate the other because the less crowded nature of the particles in one direction. So these particles were focused more towards moving along y direction because they were more crowded along y direction. There possibly could be larger repulsive forces along y direction when compared to x. Many such observations can be made when you have an interactive platform for simulating your MD behavior of the particles. So let's get back to the slides now. So before I conclude, I'd like to just recapitulate, or I would like to just give you an overview of what all we have done in this particular session. So we started with recapitulating all the elements in the algorithm that we have already discussed, and then we have taken some time to understand about cutoff radius and minimum image convention. We've also spent a little amount of time in initialization, and then we've seen a pseudo-code and a simple algorithm for molecular dynamic simulations in 2D, and then the Excel model of implementing molecular dynamic simulations. So this is for today, and in the next class we will have possibly some overview about initialization, and then we'll move on to the statistical mechanics aspect of MD simulations. So thank you all. I'm open for the questions.
Okay, Prem, I just have one small question.
Yes,
have you considered other wordlets, other algorithms also, other than wordlet, before getting into wordlet, beam and something like? I just started going through MD simulation last week.
So there is something called simplified velocity overlay scheme.
Yes.
So, or modified velocity overlay scheme. The simulation that I've shown you actually uses that.
Correct. Okay, before before finalizing this wordlet algorithm, have you what was the basis of finalizing this wordlet algorithm? Like, how is it better for something, or as compared to your with respect to your process, or is it converging quickly, or is it something like that?
Actually, the reason why I've used modified velocity overlay scheme is I want to have a simplified version of velocity upgradation process. So modified velocity overlay algorithm actually is a very simplified version. And if you could recall, velocity overlay scheme requires force in the present step as well as force in the previous step for updating velocities. So
Exactly, yes.
calculating force in the present step is a little cumbersome process. So I wanted to avoid that. So instead of taking the average of present step force and the previous step force and calculating upgrading velocities, I've taken only the previous step force. So for that very
Okay.
functionality, I've used the modified version. So obviously you are reducing the efforts from your side and you can't expect more higher level of accuracy from that.
Correct. Exactly.
And we also have better schemes than velocity overlay also, which were now being used most often. And I've not done a study as such on which scheme actually works better in upgrading velocities and positions. But as you said, definitely it will have a role to play in optimizing and bringing the solutions faster towards a faster convergence.
Okay, but ultimately you will be simulating the laser ablation process with this, right?
Yeah, I'm planning to.
Okay, okay.
So others, if
Guys,
you
we
have
have.
given a thought.
Okay, go ahead, go
Sorry,
ahead.
Anup, you can proceed.
No, I just wanted to tell everyone that we still have good 10-12 minutes. So if anyone has any queries, you can please share it right now itself. It is
Yeah.
better that queries get shared on public platforms so that everyone can learn from your doubts as well.
Yeah. In the meanwhile, I also want you to give a thought on this. If you have made any guesses, you can venture them out. So why am I just subtracting the mean value of all the velocities from every particle's velocity? I'm doing it for both x and y directions. Why am I doing that? If you had given a thought on it, and if you want to share something on it, you're most welcome.
Is it because you want to bring the average momentum to zero and that makes the system in equilibrium?
Yeah, that is the intention. So if I don't do this, all my particles together would try to move along x direction or y direction or in different combinations of x and y direction. I don't want that particular effect to be focused or implemented in my scheme. So I just wanted to have a stationary and stagnant system in which the walls are not moving, but only the particles are moving. So that's the intention. Any other questions or doubts from your
Can
end?
you explain it again? Can you explain it again? Why minus?
Yeah, say for example, I have particle 1 with x direction velocity as 2. Particle 2 has got x direction velocity as 6. So the average would come to 4. If there are only two particles in the system, then the system altogether, both the particles would move in x direction, and that would also take my system towards some displacement in x direction. So system as a whole is now trying to move along x direction. So if one particle is trying to move in x direction, in positive x direction, some other particle should counteract its motion so that overall effect of particles movement in the system or the net amount of displacements in the system should be 0. Otherwise, the system is tending to move from one place to the other place, literally. So we will do this whenever we are dealing with stationary systems. And if we have a problem statement itself on a dynamic system, like if a system itself is moving, say for example, you throw a ball and ball is full of atoms and heating process is happening in the ball and the ball is moving from one place to the other place. So all the particles were moving in with one particular direction. Moreover, the particles were also trying to vibrate in different random directions within the system. System itself is moving and the particles within the system are also moving. In that case, we'll not take this implementation. We'll not subtract this mean values.
Okay, understood. Yeah.
Hello.
Okay. Hello?
Hello. Yeah, hi, Prem.
Yes, you're audible.
I'm Ankit speaking. So,
Okay.
because of some force, we are getting some velocity.
Yeah.
Yeah. So, after that, if you modify that, then actually it affected the actual effect which is coming because of that force.
Sorry, Ankit, could you repeat that? I'm not clear on what you're
You
asking.
have taken the hello. Yeah, you have taken the
Yeah, yes, Ankit.
two particle system now. So one is
Yes.
moving with +2 in x direction, other is moving with +6 in X direction. So
Yeah.
if we say it is happening due to some force which is acting on these particles.
Yes.
So, but if we have subtracted by mean value, then one is moving it. It looks like one is moving +2 and other is -2. So it's
Yeah.
actually not exactly reflecting the effect which is caused due to the actual force which is acting on the these particles.
Yeah, that's an interesting question to answer, in fact. See, all the velocities that I have here are created by me. So I have created the random velocities for all the particles, and my intention
Yeah,
here is
initially you
just
have
to
created
keep the
that.
system. Yeah, initial.
Yeah. So after, so this is for only initial system.
Yes, this is only for the initial step.
Okay. After
So
that, they will
initially I
move
don't
in
want it.
random without any manipulation.
Yeah, and will not touch upon any of these velocities and will not use this particular scheme anymore once we set the particles into second step or second iteration. This is only the initialization part.
Okay. Yeah, then.
Yeah, I hope that answers your question.
Yeah.
Okay.
Guys, if there are no more queries, we can wrap up the session. Okay, I think every